Hello everybody. All right, so we're going to talk about 1.3 today, finding limits analytically. And before we get into it, it is the beginning of the AP course, so I just kind of wanted to highlight four methods or four things that AP Calc students should be pretty competent with, that the graders will probably look for. So, especially if you're considering, or if they're considering giving you partial credit, anything that you can do that shows that you have knowledge in these four areas is awesome. So, for AP Calc, things that students should be good with. First is algebraic manipulation. So just your algebra skills. Can you do algebra basically? Factoring, canceling, substitution, when you're solving equations or simplifying expressions, being able to do that without too many flaws. That's important. Second is graphical representations. Third, numerical analysis. And fourth, written explanations. So you will be asked to write occasionally. So knowing how to do something, forwards and backwards, and actually being able to explain what it is that's going on is going to be very helpful. So anyway, algebraic manipulation, being able to represent things graphically, working with the numbers, and then written explanations. All right, so now we're going to focus primarily on the first two today in the finding limits analytically portion. Okay, and now for finding limits, so let's go ahead and kind of write down a roadmap before we get into it. Okay, so steps for finding limits algebraically. First and foremost, you try to just substitute. Can you just plug it in? That's the question. Okay, so if you can just plug in the value of x for the limit and there's no issues, go ahead and do it. You're good to go. If not, then especially if you have a rational expression, your next best bet is to try to factor and cancel, then resubstitute. Okay, so factor and cancel, and then try resubstituting the value. If 1 and 2 fail, then another option we have is to now consider a graph or a table. Okay, so we'll go through these modes here and see if we can figure out some of these examples. Okay, so let's go ahead and look at this problem here. Let's say we want to find a limit as x approaches 2 for x squared plus 2x minus 15 all over x squared minus 3x. Okay? So first, we know that we're interested in what's going on as this function gets really close to 2. And if we're able to just plug 2 in, we're going to do that because that'll be the answer. So if I'm looking here, plugging in 2 should be fine because if I plug 2 into the denominator, you're not going to get 0. So if you plug 2 in, so you're going to have 4 plus 4 minus 15 all over 4 minus 6. So what is that? 8 minus 15. That's negative 7 over negative 2. So here we get 7 over 2 or 3.5. Okay? So that would be the answer for that example. Pretty easy, right? So now let's take a look at what happens if we switch things up a little bit. So same problem, but we're just going to explore what happens at different x values. So let's change it to the limit as x approaches 0 now for the same equation. So for x squared plus 2x minus 15 all over x squared minus 3x. Okay? So again, if we're just following our steps here, you're going to think, all right, can I plug 0 in? And right here there's an issue, right? Because if you plug 0 into the denominator, you cannot divide by 0, because that's what you get down there. So the next option, we're going to try to go ahead and factor and cancel, and then see if we can substitute 0 in. Okay? So let's see what happens. So notice I'm still using the notation, the limit as x approaches 0. Okay? And I'm just going to keep, because I'm not plugging anything in, I'm not actually figuring anything out yet, I'm just manipulating it. So we're still technically finding a limit. So then here we're going to get x plus 5 times x minus 3. Okay, down here you can take out an x as a GCF. Okay, and then you get x minus 3's cancel out. Okay, and so we've factored, we've canceled, and so what we've turned this original problem into is the limit as x approaches 0 of x plus 5 over x. Okay, so let's see, can I plug 0 in now? Here we get 5, down in the denominator we get 0. Still doesn't work, okay, because you can't divide by 0. So the next option is to perhaps consider a graph. So let's take a look at what the graph looks like. So if I look at the graph of y equals x plus 5 over x, okay, hopefully you remember how to graph your rational functions. If not, that's something you probably need to review because that's pretty important. Let me know if you need some help with that. But your vertical asymptote is going to be x equals 0. So obviously that's why we're having issues finding the limit at that value, right? There's a horizontal asymptote. Since these have the same degree, you can just divide the leading coefficients, which is 1 and 1 for the denominator. So you're going to get y equal to 1. The x-intercept. X-intercepts. If you set this equal to 0, right, x plus 5 is going to give you an x-intercept of negative 5. A y-intercept, we don't have any because we have an asymptote there. So here's what it looks like, roughly. Okay, and since this denominator gave us the vertical asymptote of x equals 0, since it's just to the first power, anytime this is odd, remember that these are going to have opposite behavior on either side of the asymptote. So if we're going down on the left-hand side, we're not going to be going down on the right-hand side. We're going to be going up. So it's going to look something like this. All right, and so now, remember when we did limits graphically, we want to explore going to, so here's 0, right? If I go to x equals 0 from the left-hand side, it looks like I'm going down, right? The graph is heading down towards negative infinity. If I approach x equals 0, let me write it that way. if I approach x equals 0 from the right-hand side, it looks like I'm heading up towards positive infinity, okay? And so because these go different directions, okay, they're not heading towards the same value, then we're going to say that the limit does not exist, okay? So that one was a little bit more involved because you had to think about things in a couple of different ways. All right. Let's do one more limit example with manipulation here. If you kind of understand what's going on, you probably could guess what the other one is going to be. So let's say we want to find the limit as x approaches 3 for the same problem, x squared plus 2x minus 15 all over x squared minus 3x. And cannot plug in 3 because you get 9 minus 9, which is 0, can't divide by 0. So we're going to fast forward a bit, okay? We're going to do the same exact process that we did earlier for example 2, and we know that it's going to become x plus 5 over x, because if we factor and cancel, we're going to get the same thing. The only thing that's different is we're looking at a different x value right here. Instead of 0, it's 3. Okay? So we have the limit as x approaches 3 of x plus 5 over x. Okay? And now can you plug this in? Looks like we absolutely can. Numerator we get 8, denominator we get 3, and there we go. Okay? So for the first example and the third example, we actually get some answers. The second one, we had a limit that did not exist. Okay? So now, one of the things too that'll be helpful is for you guys to have some insight. So if you just look carefully at the original denominator, right? Knowing that this factors as x times x minus 3, right? Remember that that's in the denominator. You can see right away that x can never be 0 or 3. That's the domain for this rational function. So anytime we have a limit that features these values, like we did for example 2, see how we have the limit as x approaches 0, and we know right away x can never be 0, right? That means we're going to have to do a couple of things to try to figure it out. Okay? Same thing with this one. We know x can never be 3, which is what we're doing here in the third example. And so we can't directly plug it in, but after we factor and cancel, right? I didn't write that step because it was the same step. Now we're able to plug it in. Okay? So that's kind of the roadmap, especially for rational functions here. Let's do a couple more quick ones. Let's say we have the limit as x approaches pi for the sine of x over 2. Okay? So first, can you plug it in? Sine of pi over 2? Absolutely. Right? Hopefully you remember your unit circle. If not, you're going to have to review that. That's huge, right? So sine of pi over 2, that's just the y-coordinate at 90 degrees. The y-coordinate there is going to be 1. Okay? And so we're done. The sine of pi over 2 is 1. You can plug in pi. That one's pretty easy. Okay? Let's look at example 5. Let's say we have the limit as x approaches pi over 2. And let's do secant of x over 2. Okay, so we're taking the limit of the secant of x over 2 as x approaches and gets near pi over 2. So can we plug it in? So let's see what happens if I do that. So this is going to be the secant of pi over 2 over 2 and remember that when you're dividing by a number, you can just change it to multiplication as long as you multiply by the reciprocal. So pi over 2 divided by 2 is really the same thing as multiplying it by a half. So if you have a hard time with these and you sometimes make the mistake of canceling the 2's out or something silly like that, remember to try this first. Then you'll see that this is just pi over 4. Okay? So now the question is, can we figure this out? Because if we can, then we're done. That's our answer. If not, if it doesn't exist or something like that, then we're going to have to think things over again. So pi over 4, I know the coordinates, so I'm always using my unit circle. The coordinates for pi over 4 are root 2 over 2, root 2 over 2, right? And I know that for secant, really it just means to do the reciprocal of the cosine or the x value. Well, the cosine or the x value is right there, okay? That's root 2 divided by 2. So we're just going to do the reciprocal, which is 2 over root 2, okay? And if you rationalize that, you're going to get just root 2. All right? So a couple of different examples. Usually fractions or rational expressions are the ones that require the most thinking. But all right, so let's go ahead and move on to some basic properties of limits. All right. So here are some basic limit properties that you guys need to work with and be comfortable with. So assume, okay, let's go ahead and just write out the whole thing. So let B and C be real numbers. N is a positive integer. And F and G are functions with the limit as x approaches C of f, let's just call that L, and the limit as x approaches C of f of x will go K. Okay? So how can we work with some multiple limits or multiple functions, multiplying them, adding them, things like that, knowing that we have a limit at this value for f, whoops, and this is supposed to be a different function g. Okay? So first property, let me go ahead and over here now. The limit as x approaches c, and let's say we just have a number multiplied times a function. Right? Well, this is just a constant. Okay? So all it's going to do is multiply the original function by this value, and therefore it will also multiply the limit by that value. Okay? So since we know, I mean, really what you can do is this. You can pull out the constant, think of it this way. Okay, since this is just multiplying whatever the limit's going to be anyway, this becomes L, and there you have it. So all you need to know is if you have a constant, really you're able to just pretend the constant's out here, and then you just, since we know that this is equal to L, you can take B times L for that first property. Okay, and then similarly, these other ones, let's say we have the limit as x approaches c of a sum or a difference of functions. Okay? If we already know the limit for f and the limit for g, if we're adding here, we're just going to add the limits together, and we know that the answer for the limit of f is L, and the answer for the limit of g is k, and so that would be the second property. And this actually works for subtraction as well, so let's just go ahead and do that instead of writing this out twice. All right. Next, let's say I want to do the limit as x approaches c, and we're multiplying two functions. Okay. same idea. If we're adding or subtracting, you just add or subtract the limits. If we're multiplying, then you can just multiply the limits. So you have L times K. Fourth one. The limit as x approaches c, and let's say we're dividing. I think you're probably figuring out where this is headed, right? If we're dividing two functions and we know the limit up there, we know the limit up there, you're just going to divide the two limits, which were L and K. My laptop went on standby, just making sure that we're still recording here. Okay. And fifth one, if we have the limit as x approaches c for f of x, and let's say that that's raised to a power, you guessed it, if we know the limit for f is equal to L, then we can just raise L to the nth power. Okay? Now it's important to mention, for this one here, I forgot to add this in because I saw my laptop shut off, provided that k does not equal 0, right? Because let's say the limit for g was equal to 0, well, you can't divide by 0, and then in that case it doesn't make sense. All right? Okay. So last example, tied to these properties. Hopefully this will be pretty quick. Well, it's one, but it's several parts. But so what is this? Example 6? All right. So let's say the limit as x approaches c of f of x equals 3 over 2. And the limit as x approaches c for g of x, let's say that equals 1/2. Okay? And so let's just do several quick ones here. Let's say I want to find the limit as x approaches c for 4 times f of x. Okay? Now it's worth mentioning, I know I'm going through these quickly, you should get in the habit of trying to figure things out. If you kind of have an idea of where things are headed, the more connections you can make on your own rather than having me make them for you, the better you're going to be in the long term. So if you kind of know what to do here, pause it, think about it for a sec, try to come up with an answer and see if you're on the right track. And if you're not, no big deal. Hopefully as I go through it, a light bulb will go off and you'll start to get it. So yeah, this is just like the first property. Since we have a constant of 4 in there, you can just take 4 times the limit of f of x, okay? And so that's just going to be 3 over 2. And if you simplify that, you're going to get 6. Okay? B. Let's say we have the limit as x approaches c of f of x plus g of x. Okay? Well, if we're adding two separate functions, but we know both of their limits, you're just going to add those two limiting values together. So here we get 3/2 plus 1/2, which is 2. Okay? C. Let's say we have the limit of x approaches c, or the limit as x approaches c, and let's do f of x over g of x. Okay? So, again, we know both of these limiting values. For f, the limit was 3 over 2. For g, the limit was 1 over 2. And so you can just do the math there. You can change that to multiplying by the reciprocal if it helps. And so your answer there is going to be 3. Okay? So part A answer was 6, part B answer was 2, and part C answer was 3. And I think that might have gotten cut off just a bit. There it is. Okay? All right. Thank you for tuning in. We'll see you in class next time.